The presence of a common matchbox in a kitchen drawer represents a deceptive state of peace, hiding a localized chemical apocalypse that can be triggered by a single mechanical motion. Within the rough, dark strip on the side of that box lies a substance defined by a profound and volatile thirst for equilibrium, a material that occupies a unique and paradoxical position in the history of human survival. This is phosphorus, an element so chemically aggressive that it does not exist in its pure form anywhere on the surface of the planet. Yet it serves as the literal backbone of every strand of DNA and the primary driver of global food production. To strike a match is to perform a controlled experiment in atomic instability, initiating a chain reaction that transforms mechanical friction into thermal energy. This exploration of the fundamental elements that build and sustain our reality is part of a broader investigation into the hidden mechanics of the universe.
Subscribing to this channel and sharing a perspective in the comments helps maintain the rigorous depth of these scientific narratives, ensuring that the complex stories of our material world continue to be told. The transition from a dormant state to an active flame on the side of a matchbox is an exercise in thermodynamic transition. The dark coating on the box contains red phosphorus, a stable allotrope of the element that consists of long, polymerized chains of atoms. In this state, the phosphorus is relatively safe, capable of sitting in a room at 70 degrees Fahrenheit for decades without reacting. However, the moment the match head, which contains an oxidizer like potassium chlorate, is dragged across this surface, the kinetic energy of the friction creates a localized spike in temperature. This heat, reaching approximately 350 degrees Fahrenheit in a microscopic area, is sufficient to break the chemical bonds of the red phosphorus. For a fraction of a second, the red phosphorus is converted into its much more dangerous sibling, white phosphorus. White phosphorus is the unmasked version of the element, consisting of 4 phosphorus atoms arranged in a tight tetrahedral shape, P4. Because the bond angles in this shape are compressed to 60 degrees, a configuration that is geometrically uncomfortable for the atoms, the molecule exists in a state of extreme tension, much like a tightly coiled metal spring held by a fragile latch. The moment these P4 molecules encounter the oxygen in the atmosphere, the tension is released. The phosphorus reacts so violently with oxygen that it ignites spontaneously, producing a brilliant white light and a dense cloud of phosphorus pentoxide, P4O10. This localized flash of heat then ignites the combustible chemicals in the match head, resulting in the flame we use to light a stove or a candle. The matchbox is not merely a container. It is a specialized laboratory designed to manage an element that essentially hates to be alone and will burn its way through the atmosphere to find a partner. This chemical restlessness is the reason phosphorus is described as a double agent in the story of life. While its pure form is a lethal incendiary, its oxidized form, phosphate, is the primary architect of biological energy. Within the human body, phosphorus functions as the central component of adenosine triphosphate, or ATP. To understand the importance of ATP, one must view the human body not as a static object, but as a high-performance electrical machine that requires a universal currency for every move it makes. Every time a muscle fiber contracts, every time a neuron in the brain fires an electrical signal, and every time a cell repairs its membrane, a payment of energy is required. This energy is stored in the chemical bonds between the phosphorus atoms in the ATP molecule. The structure of ATP is comparable to a spring-loaded trap. 3 phosphate groups are linked together in a row, each carrying a negative charge. Because like charges repel each other, similar to trying to push the matching poles of 2 powerful magnets together, these phosphate groups are constantly pushing away from one another. They stay connected only because of a high-energy chemical bond. When the body needs energy, an enzyme trips the trap, breaking the bond of the 3rd phosphate group. This release, known as dephosphorylation, provides a precise, standardized burst of energy that the cell can use to perform work. The resulting ADP, adenosine diphosphate, is then sent back to the cellular recharging station, the mitochondria, where the phosphorus is reattached using energy from food. This cycle is so relentless that a human being will cycle through their own body weight in ATP every single day. We are, in a very literal sense, walking phosphorus-powered batteries. The dual nature of phosphorus extends into the foundations of global civilization. In the modern world, the availability of phosphorus dictates the limit of human population. For nearly all of human history, agriculture was limited by the bottleneck of soil nutrients. Phosphorus is a sedimentary element, meaning it does not have a gaseous phase. Once it is used by a plant and that plant is eaten or harvested, the phosphorus is removed from the local soil. Before the industrial era, farmers relied on the slow, natural recycling of manure and bone meal to replenish the fields. This changed in the 19th century with the discovery of massive deposits of phosphate rock and guano, the accumulated droppings of seabirds. The transition to industrial phosphorus was a turning point for the human species. By treating phosphate rock with sulfuric acid, H2SO4, chemists created superphosphate, a highly soluble fertilizer that allowed for the intensification of farming. Today, approximately 90% of all phosphorus extracted from the Earth's crust is used for fertilizer. Without this consistent injection of phosphorus into the global food system, the current population of 8 billion people could not be sustained. The supermarket shelves, filled with grain, vegetables, and meat, are essentially a processed form of ancient marine phosphorus that has been brought back to the surface. We have built our global survival on the management of an element that is as essential as water, but far rarer in its accessible form. However, the management of this caged madness carries heavy consequences. Phosphorus is not just a nutrient for crops. It is an incredibly efficient stimulant for life in general. When excess phosphorus from fertilized fields or industrial waste leaks into H2O systems like lakes and rivers, it triggers a phenomenon known as eutrophication. The algae in the water, which were previously limited by a lack of phosphorus, suddenly enter a state of explosive growth. They create massive blooms that cover the surface of the water, blocking out the sun. When these algae die, their decomposition consumes all the dissolved oxygen in the H2O, creating dead zones where no fish or other aquatic life can survive. It is a stark reminder that phosphorus is a master of extremes. In the right concentration, it feeds a continent, but in the wrong place, it suffocates an ecosystem. The paradox of phosphorus is perhaps best summarized by its role in our skeletal structure. Our bones and teeth are not made of simple calcium, but of a complex mineral called hydroxyapatite, which is primarily composed of calcium phosphate. This mineral provides the rigid, structural framework that allows us to stand against gravity. While the iron in our blood carries the oxygen and the carbon in our tissues provides the organic structure, it is the phosphorus that provides the mineral rebar of the human frame. We are structured with the same material that we use to light matches and fertilize corn. To look at a matchbox is to look at the entire human condition summarized in a small piece of cardboard. It is the story of an element that was forged in the hearts of dying stars and delivered to a cooling planet where it learned to hold our genetic code and power our muscles. It is a material that demands constant vigilance because of its inherent nervousness and its desire to return to a state of flame. We have taken this 13th element and turned it into the silent guarantor of our survival, using it to build our bones, drive our thoughts, and feed our billions. The matchbox is not just a tool for fire, it is a handheld piece of the cosmic lottery, a reminder that the most essential components of life are often those that are most difficult to contain. We live in a phosphorus-dependent world, balanced on the thin, rough edge of a strike strip, where the cold fire of the alchemist's lab has become the invisible foundation of the modern age. The distribution of matter throughout the universe is characterized by a profound chemical hierarchy, where the most essential building blocks of life are often the most difficult to manufacture in the cosmic furnace. While elements like hydrogen and helium were produced in the immediate aftermath of the Big Bang, and carbon and oxygen are churned out in vast quantities by nearly every medium-sized star, phosphorus is a rare and elusive guest. In the grand inventory of the cosmos, phosphorus, P, is a significant rarity, occupying a position of scarcity that makes its presence on Earth appear as a statistical anomaly. To understand the origin of this element, one must look toward the final, violent stages of massive stars, those with at least 20 times the mass of the Sun, where the conditions of pressure and temperature reach a threshold capable of forging the 15th element. Within these gargantuan stars, phosphorus is produced through a specific nuclear pathway known as the neon-burning and oxygen-burning phases. This occurs in the deep interior layers of the star, shortly before it collapses into a supernova. The process can be explained through the analogy of a high-stakes construction project occurring inside a collapsing building. As the star exhausts its lighter fuels, it begins to burn heavier elements to maintain the outward pressure that prevents its own gravity from crushing it. Phosphorus is created when a silicon nucleus captures a proton, or when neon and magnesium nuclei undergo specific transformations. However, there is a fundamental law of nuclear physics known as the odd-even rule, or Harkin's rule, which dictates that elements with an even atomic number are significantly more abundant than those with an odd atomic number. Because phosphorus has 15 protons, it is inherently less stable and more difficult to produce than its even-numbered neighbors like silicon, 14, or sulfur, 16. It is like a rare, custom-made structural component in a warehouse otherwise filled with mass-produced parts. When these massive stars finally exhaust their nuclear potential and explode in a supernova, they eject their internal contents into the interstellar void. Because phosphorus is produced in such small quantities, often 10 to 100 times less than carbon or nitrogen, the clouds of gas and dust that eventually form new solar systems are traditionally phosphorus poor. This creates what astrobiologists call the _17_. If phosphorus is the limiting factor for life, because it is necessary for the construction of DNA and the management of cellular energy, then the rarity of this element in the universe might be the primary reason why life itself is not more common. The Earth's possession of enough phosphorus to support a global biosphere of 8 billion humans and trillions of other organisms is the result of a specific delivery mechanism that bypassed the standard geological constraints of the planet. During the early formation of the Earth, the planet was a molten ball of liquid rock and metal. Because phosphorus has a chemical affinity for iron, a property known as being siderophilic, much of the planet's initial supply of the element followed the iron as it sank toward the center. This process effectively locked the primordial phosphorus away in the Earth's core, 1,800 miles beneath the surface, where it was completely inaccessible to the chemical processes of the surface. If the Earth had relied solely on its internal supply, the surface would have remained a phosphorus desert, devoid of the nutrients required to trigger the leap from simple chemistry to complex biology. The rescue of the Earth's biosphere came from the sky. During the period known as the Late Heavy Bombardment, approximately 4 billion years ago, the Earth was subjected to a relentless barrage of meteorites and asteroids. These were not mere rocks, but specialized chemical capsules from the outer reaches of the solar system. A specific type of meteorite, known as an iron-nickel meteorite, contained a rare mineral called shrapnel, Fe(Ni)3P. This mineral is a phosphide, meaning it contains phosphorus in a state that is not yet bonded with oxygen. The arrival of shrapnel on the early Earth was a transformative event for prebiotic chemistry. On the modern Earth, most phosphorus is found in the form of apatite, a phosphate mineral that is as hard and insoluble as a stone. If you place a phosphate rock in a stilled pool of H2O, nothing happens. The phosphorus remains locked in the mineral lattice, useless for any biological reaction. However, shrapnel is different. When this _quote_19_ comes into contact with H2O, it undergoes a slow chemical reaction that releases phosphorus in a soluble form, specifically as phosphites and polyphosphates. This process can be compared to the difference between a sealed stone jar and a time-release vitamin. The shrapnel provided a steady, accessible supply of reactive phosphorus to the primordial oceans. In these early _20, the presence of soluble phosphorus allowed for the formation of the first nucleotides and the first energy-carrying molecules. Without this specific cosmic delivery of meteoritic minerals, the chemical evolution of the planet would have stalled. Phosphorus acted as the _21, the one ingredient whose absence prevents the entire recipe from being completed. It was the _22 that allowed Earth to win the game of biological complexity. The rarity of phosphorus in the cosmos also shapes our understanding of the _23_. Because phosphorus is only produced in specific types of supernovae, and because its delivery to planets depends on the chaotic movement of meteorites, not every solar system is equally capable of supporting life. A planet might have H2O, an atmosphere, and a stable temperature, but if it lacks the specific _24__ from cosmic impacts, its oceans will remain sterile. This makes the phosphorus in our own bodies, the atoms currently holding our genetic code together, a direct physical link to a rare stellar explosion that occurred billions of years ago, and a specific meteorite that successfully navigated the hazards of the early solar system to land in our oceans. The chemistry of phosphorus on the early Earth was further complicated by its behavior in the absence of oxygen. In the modern atmosphere, phosphorus is almost always found in its most oxidized state as phosphate, PO4. But in the ancient, oxygen-free atmosphere, the element could exist in more __25__ and highly reactive states. This reactivity was essential for the creation of the first metabolic pathways. It is through phosphorus that life learned to __26__ energy. The invention of the phosphate-based bond was a masterclass in molecular engineering. By linking phosphorus and oxygen atoms together in a chain, the first cells created a way to store potential energy in a stable but accessible format. This molecular __27__ is the universal foundation of all known life. Whether it is a bacterium living in a deep-sea hydrothermal vent at 300 degrees Fahrenheit, or a human brain cell calculating a complex equation, the fundamental mechanism for storing and releasing energy is exactly the same. It relies on the repulsion between negatively charged phosphate groups, a force that is held in check by a chemical bond until it is needed. This uniformity suggests that once life __28__ the utility of phosphorus, it never found a more efficient alternative. The element's rarity in the universe is balanced by its total indispensability on Earth. The geological cycle of phosphorus is equally unique because it lacks a significant gaseous phase. Unlike carbon, which moves from the air to the plants and back to the air, or H2O, which cycles through evaporation and rain, phosphorus is ___29__ It starts in the rocks, is leached into the soil, is absorbed by plants, and eventually washes into the rivers and the sea. Once it reaches the ocean floor, it settles into the sediment, where it is compressed into new rock over millions of years. This means that on a human timescale, the phosphorus we use is a finite, non-renewable resource. We are living on the legacy of the late heavy bombardment, utilizing the accumulated phosphorus of eons to support a modern population that is growing at a rate far faster than the geological cycle can replenish. To look at phosphorus through the lens of cosmic history is to see an element of profound strategic importance. It is the _30__ element that dictates the scale of life. It is the material that turned the Earth from a rocky, metallic sphere into a living, thinking world. Every phosphorus atom in the human frame is a survivor of a cosmic lottery, a piece of stellar ash that was forged in the death of a giant sun, survived a supernova, traveled through the void of space as part of a mineral crystal, and was eventually dissolved into the waters of our planet to become the carrier of our genetic memory. We are the beneficiaries of a cosmic accident, a rare moment where the scarcity of the universe was overcome by the specific mechanics of planetary assembly. Phosphorus is the limiting factor that became the liberating factor, the rare _31_ that gave us the power to grow, to think, and to build a civilization that now looks back at the stars to understand the fiery origin of its own bones and its own energy. The history of human interaction with phosphorus is a narrative that began not in the pristine environment of a modern laboratory, but in the foul-smelling, desperate workshops of the 17th century alchemists. In the year 1669, a failed merchant and amateur chemist named Hennig Brand, residing in Hamburg, was engaged in a pursuit that was common to his era: the search for the philosopher's stone. This mythical substance was believed to be capable of transmuting base metals into gold and granting eternal life. Brand's approach to this problem was governed by a peculiar and misguided logic of color association. He observed that human urine possessed a golden yellow hue, and he hypothesized that this liquid must contain a concentrated essence of gold that could be extracted through the rigorous application of heat and time. This began what is arguably the most unrefined and physically repulsive chapter in the history of scientific discovery, involving the collection of thousands of liters of urine from soldiers and local residents. The engineering of Brand's experiment was a brutal exercise in distillation and reduction. To understand the process, one can compare it to the slow reduction of a culinary sauce, but performed on a massive industrial scale, with a substance that released increasingly toxic and pungent fumes as the H2O was removed. Brand boiled the urine until it reached the consistency of a thick, dark syrup, which he then allowed to ferment and putrefy for several weeks. Following this, he subjected the resulting paste to extreme heat in a closed retort, a glass vessel with a long, downward-sloping neck. The goal was to drive out the spirit of the matter through thermal energy. As the temperature inside the furnace climbed toward 1000 degrees Fahrenheit, something unprecedented occurred. Instead of the expected gold, a heavy, white vapor began to flow through the neck of the retort and settle in the water-filled receiver. When this vapor cooled, it solidified into a waxy, white substance that exhibited a ghostly, greenish-white glow in the darkness. This was the first time in history that an element had been isolated by an individual whose name was recorded, and phosphorus was the 13th element to be added to the human inventory. Brand named it Phosphorus mirabilis, or miraculous bearer of light. The cold fire that he had discovered was not a magical property, but a specific chemical phenomenon known as chemiluminescence. At the atomic level, The white phosphorus he had produced was reacting slowly with the oxygen at the surface of the H2O, a process of slow-motion combustion that released energy in the form of light rather than intense heat. This waxy material was so reactive that the moment it was exposed to the open air, the rate of oxidation would accelerate until the substance burst into a brilliant white-hot flame. Brand had unknowingly unlocked a material that was too dangerous to be left in the open, yet too fascinating to be ignored. For several decades, phosphorus remained a high-priced curiosity, a circus trick for the European aristocracy. Brand, having failed to produce gold, attempted to recoup his losses by selling the secret of the process to other alchemists and royal courts. Demonstrations of the glowing firestone became a popular entertainment among the wealthy, who were mesmerized by a substance that appeared to be alive with its own internal light. However, the true historical drama of phosphorus shifted from entertainment to utility in the 19th century, as the Industrial Revolution sought a reliable way to create fire on demand. Before this era, lighting a fire was a laborious process involving flint, steel, and tinder. The invention of the friction match changed everything, and it was phosphorus that provided the necessary chemical hair trigger. The first commercial matches, known as lucifers, utilized white phosphorus. This was a technological leap forward, but it introduced a horrific industrial tragedy. The factories that produced these matches were filled with workers, mostly women and children, who were exposed to phosphorus vapors for 12 to 14 hours a day. White phosphorus is highly lipid-soluble, meaning it can easily pass through human tissue and bond with the calcium in the jawbone. This led to a medical catastrophe known as phossy jaw. The phosphorus effectively ate the bone from the inside out, causing the jaw to glow in the dark before eventually rotting away, leading to disfigurement and a slow, agonizing death from organ failure. This was a dark demonstration of the element's aggressive chemistry. The same material that provided the convenience of instant fire was capable of systematically dismantling the structural framework of the human body. The social and legal outcry against these conditions eventually led to the 1906 Berne Convention, the first international treaty to ban the use of a specific industrial chemical. The industry was forced to transition to red phosphorus, a safer, polymerized version of the element that is used in modern matches. This transition represented a significant engineering achievement. By simply changing the way the phosphorus atoms were linked together, from a fragile 4-atom triangle to a long, stable chain, the element was transformed from a lethal toxin into a safe consumer product. This was the moment humanity learned that the danger of an element is not just about its identity, but about its molecular arrangement. Simultaneously, a second drama was unfolding in the fields of Europe. As the population grew, the soil became depleted of its natural nutrients, leading to widespread crop failures. Scientists like Justus von Liebig realized that phosphorus was the limiting factor of agriculture. This realization triggered a desperate and ghoulish search for the element. In the mid-century, the demand for phosphorus was so high that the battlefields of the Napoleonic Wars, including Waterloo, were systematically looted for human and horse bones. These bones were ground into a fine dust and spread across the fields of England and Germany as fertilizer. This was the Great Bone Robbery, a period where the remnants of the past were literally used to feed the present. The phosphorus in the bones of fallen soldiers became the bread and potatoes of the next generation. This era of biological scavenging ended with the discovery of massive deposits of phosphate rock in places like North Africa and Florida. These deposits are the remains of ancient marine life, trillions of tiny organisms that died and settled on the ocean floor millions of years ago. By the early 20th century, humanity had moved from boiling urine and grinding bones to the industrial-scale mining of these ancient sediments. The element had moved from the shadows of the alchemist's basement to the center of global geopolitics. Today, the control of phosphate mines is as strategically important as the control of oil fields. The military application of phosphorus also evolved into a terrifying science. During the World Wars, white phosphorus was repurposed as an incendiary weapon and a smoke screening agent. Its ability to burn at 1,500 degrees Fahrenheit and its persistence — it cannot be easily extinguished with H2O because it continues to burn as long as it has access to oxygen — made it a weapon of psychological and physical devastation. It became known as Willy Pete in military slang, a substance that would stick to surfaces and continue to burn through metal and flesh alike. This represented the ultimate perversion of Brand's miraculous bearer of light, turning a biological necessity into a tool of total destruction. To trace the history of phosphorus is to see a material that has been extracted from the most humble of sources, waste and bones, to become the guarantor of our global food supply and the driver of our most violent technologies. It is a story of human ingenuity grappling with an element that refuses to be stable. We have moved from the foul-smelling experiments of Hennig Brand to the clean, high-tech world of modern agriculture. Yet the phosphorus remains the same, a restless, glowing double agent that holds the power of life and the threat of fire in every single atom. The drama of its discovery and its industrialization is a testament to the fact that our civilization is built on the management of materials that are fundamentally incompatible with our safety, yet absolutely necessary for our existence.
We have taken the cold fire of the 17th century and turned it into the invisible engine of the 21st century, proving that the secret of the alchemists was not in the gold they sought, but in the white, waxy substance they found along the way. The operation of a modern technological society is contingent upon the silent, tireless movement of phosphorus through systems that range from the microscopic interior of a human cell to the high-frequency circuits of a global communication network. This element acts as the invisible courier of energy and safety, performing roles that are so fundamental that their absence would result in the immediate cessation of all complex biological and mechanical activity. While the historical drama of phosphorus was defined by the glowing, cold fire of the alchemist's lab, the modern reality is defined by its role as a molecular battery and a precision filter for light.
To understand the hidden engine of the present, one must look past the visible surfaces of gadgets and into the atomic interactions that allow energy to be stored, transferred, and controlled with microsecond precision. The most critical function of phosphorus in the modern era occurs at the biological level, within the cycle of adenosine triphosphate, or ATP. This molecule is the universal energy currency of life, a standardized unit of power that allows for everything from the blinking of an eye to the construction of a complex thought. The mechanism of ATP is a masterpiece of chemical engineering that relies on the specific repulsion between phosphate groups. A single ATP molecule consists of a sugar and a nitrogen base attached to a chain of 3 phosphate groups, PO4. Each of these groups carries a strong negative electrical charge. Because similar charges repel each other, much like the matching poles of 2 powerful magnets being forced together, the bond holding the 3rd phosphate group to the chain is under immense tension. It is a loaded spring at the molecular level. When a cell requires energy to perform a task, such as moving a protein or pumping an ion across a membrane, it utilizes an enzyme to break that final phosphorus bond. The spring snaps, releasing a discrete packet of energy and leaving behind a molecule with only 2 phosphate groups, known as ADP. The scale of this operation is staggering. A human body at rest, maintained at approximately 98.6 degrees Fahrenheit, requires the recycling of its entire weight in ATP every single day.
This is not a slow geological process, but a rapid-fire chemical exchange that occurs millions of times per second in every one of the body's 30 trillion cells. Phosphorus is the only element in the periodic table capable of forming these specific, high-energy, yet stable bonds that can be broken and reformed with such efficiency. Without the presence of these phosphate springs, the biological world would be a static, cold environment, incapable of the rapid movement and complex metabolism that define life. This principle of energy management transitions seamlessly from the biological realm to the world of high-definition electronics. Every time a smartphone screen illuminates or a television displays a vibrant color, phosphorus, in the form of specialized compounds called phosphors or luminophores, is at work. It is important to distinguish between the element phosphorus and these luminescent materials. While not all phosphors contain the element, phosphorus-based compounds have been the historical and technical foundation of light-emitting technology. In a modern LED display, the source of light is typically a blue light-emitting diode. However, blue light alone is incapable of producing the full spectrum of color required for a realistic image. To achieve this, the blue light is passed through a thin layer of phosphor material. The physics of this process is known as down conversion. When the high-energy blue photons strike the phosphor layer, they excite the electrons in the phosphorus-based crystal lattice. As these electrons return to their stable state, they release the energy as light of a lower frequency, typically green, yellow, or red. This can be compared to throwing a high-velocity rubber ball at a series of specialized walls that absorb some of the impact and bounce the ball back at a slower, more controlled speed. By precisely engineering the chemical composition of these phosphorus-rich layers, manufacturers can control the exact wavelength of the light produced, allowing for the so-called retina displays that offer near-perfect color accuracy. If phosphorus were removed from this equation, the digital world would be limited to a harsh, monochromatic blue, devoid of the visual depth that allows for modern communication and entertainment. Beyond its role in light and energy, phosphorus serves as a critical guardian of safety in the age of the lithium-ion battery. The high energy density of modern electronics comes with a significant risk of thermal runaway, a condition where a battery short-circuits and begins to heat up rapidly, potentially reaching temperatures over 300 degrees Fahrenheit. In such an event, the plastic casings and internal components of a phone or a laptop would typically act as fuel for a fire. To prevent this, the electronics industry utilizes phosphorus-based flame retardants. Unlike older, toxic halogen-based chemicals, phosphorus retardants work through a clever mechanism of intermescence. When a phosphorus-treated plastic is exposed to extreme heat, the phosphorus compounds undergo a rapid chemical transition, reacting with the surrounding material to form a thick, non-combustible layer of char, or carbonized foam. This acts as a molecular fire curtain. It creates a physical barrier that prevents oxygen from reaching the underlying fuel and blocks the transfer of heat. This is an engineering solution that turns the potential destruction of a fire against itself. The heat triggers the formation of a shield. This allows a device to fail safely rather than turning into a projectile of fire in a pocket or an airplane cabin. Phosphorus is the reason why we can carry massive amounts of potential energy in our pockets without constant concern for spontaneous combustion. The element also plays a foundational, though invisible, role in the semiconductor industry. To make silicon, a material that is naturally a poor conductor, into a functional part of a microchip, it must undergo a process called doping. This involves introducing a precise amount of impurities into the silicon crystal lattice to alter its electrical properties. Phosphorus is the primary N-type dopant. Because silicon has 4 valence electrons and phosphorus has 15 protons and 5 valence electrons, placing a phosphorus atom into a silicon grid creates a spare electron. This extra electron is not tied to a specific bond
and is free to move throughout the material, creating a flow of negative charge. To explain this on the fingers, if a perfectly packed box of marbles, the silicon, is disrupted by adding a few marbles of a slightly different size, the phosphorus, it creates a looseness, or potential for movement where there was once none. This looseness is what allows for the creation of transistors, the microscopic switches that are the basic building blocks of all logic and memory in a computer. Every calculation, every line of code, and every digital transaction is enabled by the presence of these extra electrons provided by the phosphorus atoms embedded in the silicon. The modern internet and the entire architecture of artificial intelligence are, at their base, a series of electrical surges managed by the specific atomic structure of the 15th element. Furthermore, phosphorus is a critical component in the processing of metals and the protection of infrastructure. In the aerospace and automotive industries, phosphorus is used in electroless nickel plating, a process that coats complex metal parts with a uniform, corrosion-resistant layer. The addition of phosphorus to the nickel alloy makes the surface harder, more lubricious, and more resistant to wear. This is essential for the high-precision components of jet engines and hydraulic systems that must operate under extreme pressures and temperatures. It prevents the metal from galling or seizing up, ensuring that the heavy machinery of the industrial world continues to move with minimal friction. The paradox of phosphorus in the 21st century is that it is a material of absolute necessity that operates entirely out of sight. It is the silent regulator of the body's heat, the transformer of light in our screens, the firewall in our pockets, and the extra electron in our processors. It is a material that transitions between the organic and the inorganic with a fluidity that no other element can match. We do not think about phosphorus as we scroll through a news feed or charge a car, yet the physical possibility of those actions is entirely dependent on the caged madness of an element that was once sought as the key to gold, and is now the key to the digital and biological present. It is the hidden architecture of the modern era, a substance that has moved from the alchemist's basement to the center of every high-tech system, proving that the true power of a material lies in its ability to manage energy at the scale of the atom. Without the constant work of phosphorus, our world would be a colder, darker, and more dangerous place, lacking the energy to move and the light to see. The permanence of human civilization on the geological record is often discussed in terms of the durable structures we leave behind, such as the reinforced concrete of urban centers or the glass and plastic of our discarded technology. However, from the perspective of deep time, stretching into the millions of years, these physical monuments are relatively fragile and prone to erosion. The true, indelible signature of the modern era will not be found in the shapes of our buildings, but in a specific chemical anomaly written into the layers of the Earth's crust. This signature is defined by a massive global redistribution of phosphorus. Unlike carbon, which moves through the atmosphere in a rapid and continuous cycle, or H2O, which circulates through evaporation and precipitation, phosphorus is an element that follows a linear and largely irreversible path on a human timescale. It is a one-way traveler that moves from the solid rock into the biological world and eventually settles into the silence of the deep ocean floor. This unique characteristic ensures that phosphorus will be the primary biographer of our species, marking the moment when a biological entity began to bypass the slow, natural cycles of the planet to support a population of billions. The fundamental reason for this linear movement is that phosphorus lacks a stable gaseous phase at the temperatures and pressures found on the Earth's surface. While carbon can return to the atmosphere as CO2 and nitrogen can return as N2, phosphorus is physically tethered to the ground. It exists primarily in the form of phosphate minerals, such as apatite, which are locked away in the Earth's crust. Under natural conditions, the release of this phosphorus is a process of extreme geological patience. It requires the mechanical force of freezing H2O to crack the rock and the chemical action of weak acids in the soil to slowly dissolve the mineral lattice. In a world untouched by industrial technology, this process is so slow that the growth of forests and the complexity of ecosystems are strictly limited by the amount of phosphorus that is liberated each year. It is the quote 72 that keeps the biosphere in balance. Humanity, however, has fundamentally altered this rhythm. In the late 1800s and throughout the 1900s, the industrialization of mining allowed us to accelerate the release of phosphorus by a factor of hundreds. We have effectively, quote, 73 the planetary supply. By mining millions of tons of phosphate rock from concentrated deposits, primarily in regions like Morocco, which holds roughly 70% of the world's remaining high-grade reserves, we are taking phosphorus that was meant to be released over the next 100 million years and injecting it into the global food system in a single century. This massive pulse of the 15th element is the engine of the quote, 74 but it is also a process of chemical depletion. Once this phosphorus is spread onto a field, absorbed by a crop, consumed by a human, and eventually flushed into a sewer system, it begins a relentless journey toward the sea. This journey through the global watershed is an exercise in thermodynamic inevitability. Rainwater strikes the fertilized fields, picking up soluble phosphorus molecules and carrying them into the smaller streams, which merge into the great river systems like the Mississippi, the Amazon, or the Yangtze. From there, the phosphorus is discharged into the continental shelves of the world's oceans. Unlike the nutrient cycles on land, the phosphorus in the deep ocean is effectively lost to the biosphere. It settles into the abyssal plains, where it is buried under layers of marine snow and sediment. This creates a quote, 75 To return this phosphorus to the surface, where it can be used again, the planet must employ the slow, grinding machinery of plate tectonics. It requires the ocean floor to be subducted under a continent, melted in the mantle, and eventually pushed back up as a new mountain range, a cycle that operates on a timescale of 10 to 50 million years. The result of this industrial acceleration is the creation of a, quote, 76 in the Earth's sedimentary record.
If an explorer from the distant future were to use a spectrometer to analyze a vertical slice of the Earth's crust, they would find a sharp, anomalous spike in phosphorus levels corresponding to the brief period of human industrial dominance. This layer would be found not only in the ancient agricultural zones, but also in the strata beneath our vanished cities. Humans are phosphorus concentrators. We collect the element from across the globe and store it in our bones, our waste, and our cemeteries. Even after the concrete has eroded and the steel has rusted away into a red dust, the chemical ghost of our presence will remain. The soil in the footprint of a former metropolis like Tokyo or New York will be thousands of times richer in phosphates than the surrounding wilderness. This chemical autograph is virtually indestructible, serving as a permanent record of where we lived and how many of us there were. We are currently living in the era of peak phosphorus, a period of precarious abundance. Unlike oil, for which there are alternatives like solar or nuclear power, there is no substitute for phosphorus. It is a biological requirement that cannot be bypassed by any known engineering or genetic modification. The DNA of every living thing requires a phosphate backbone, and the energy of every cell requires the ATP cycle. This means that the future of human civilization is directly tied to the remaining deposits of phosphate rock. As the high-grade sources are exhausted, the cost of food production will rise, and the geopolitical importance of the phosphorus-rich nations will eclipse that of the oil-rich nations.
We are approaching a geological wall where the one-way trip of this element begins to threaten the stability of the global food supply. Through the millions of years that will follow the eventual decline of human industrial activity, the phosphorus we have redistributed will continue its silent journey. The phosphorus layer in the rock will be buried under new sediments, becoming a stratigraphic marker of the Anthropocene. Eventually, the slow movement of the tectonic plates will carry these phosphorus-rich sediments back into the Earth's interior. They will be subjected to pressures exceeding 1 million pounds per square inch and temperatures over 2,000 degrees Fahrenheit. In this furnace, the phosphorus atoms will be purged of their biological history and reintegrated into new minerals, ready to begin the cycle once again when they are eventually pushed back to the surface millions of years from now. The final chapter of phosphorus's legacy on Earth will be written when the Sun expands into a red giant, approximately 5 billion years into the future. As the temperature of the Earth's surface climbs toward 1,500 degrees Fahrenheit, the oceans will evaporate and the crust will begin to melt. At this threshold, the chemical bonds of the apatite and schreibosite will finally be broken by the sheer intensity of the solar radiation. The phosphorus that once held the genetic code of humanity and the energy of our thoughts will be vaporized into a brilliant, glowing gas. It will return to the interstellar medium, drifting through the void as the same stellar ash it was when it first arrived on the early Earth. In this cosmic perspective, the history of phosphorus is a story of a rare and precious resource that was used by a biological species to briefly illuminate the darkness of the universe. We have taken an element that was forged in the death of massive stars and used it to build our bones, feed our children, and light our screens. We have moved it from the deep rock to the center of our lives, creating a chemical legacy that will outlast any monument of stone or steel. Phosphorus is the element of the bottleneck, the material that dictates the limits of what is possible. It is a substance of absolute utility and uncompromising reality, a silent architect that has governed every stage of human evolution. Every match we strike, every meal we consume, and every breath we take is a utilization of this rare space mineral that successfully navigated the hazards of the cosmos to land on our planet. Phosphorus is the enduring signature of life, a glowing thread that connects the beginning of the universe to the ultimate future, proving that the most profound forces in the world are often those that are most difficult to keep in place. It is our most chesty and permanent biographer, a material that will remain as a witness to our existence long after the last human voice has faded into the silence of time.